handling user input, right? So the user needs to interact with us, with the controller. Typically, excuse me. Thank you. For most part, in this, at least this first 3 weeks, we're going to be talking mostly with user input, textual input as they interact with the keyboard. Yeah, so we'll talk about two types of controllers, as I mentioned earlier: synchronous controllers and asynchronous controller. In a synchronous controller, right? There's going to be a very well choreographed sequence of operations, right? Usually, it takes the form of the system prompts you, right? You answer the prompt, right? The system processes that prompt, and then it prompts you again. Right, so it takes turns as you and the system interact with one another, and the controller is responsible for implementing this choreographed interaction. Yes, it is not the user who has control over the sequence of events. It is the controller who controls this sequence of events. Yeah, so it's very good for when the rules of engagement are very well defined, right? That this happens and then this is how it reacts, and it's very simple. And it's perfect for what we're building this week and the next couple of weeks for the games, right? Board games, and has a very well choreographed set of actions. So some pre-baked rules. There are perhaps it could be represented as a finite state machine, right? And depending on what state you are, there's only a very well-defined number of events that allow you to navigate to the next state. Yes, and the controller controls all this transition between the events. We are going to be looking at regardless of whether there's a synchronous or asynchronous controller. We're going to be drilling into you for this week and for the next couple of several weeks. That we're always going to be looking for being able to replace any part of the application, right? We're going to look at a controller today, but we're going to always look for a means to be able to replace it with other controllers, right? Or if we're designing a model, we're going to always be looking to ways that we could replace the model, okay? So that it's configurable, so that at some point you should be able to say, oh, well, I want to try this other controller. See if it's better. Or let me try this other way of implementing the model, right? If for anything, what's going to allow us to do is to later on make this much easier to test, right? To be able to replace the different parts and simulate them. And it says, well, I don't have really access to the database or the network. Well, could I replace that, right? And the strategy is going to be that instead of me directly accessing the database or the network, instead, that implementation is going to be, of accessing the network or the database, is going to be wrapped into a class that implements a very well-defined interface. Yes? Right? So never our code is going to be dependent on any specific low-level actual invocation of the database. Instead, it's going to be written in terms of some high-level interface, right? Which some implementation implements using the low-level interaction with the network or the database, right? What that's going to allow us to do is going to say, well, I can now remove that dependency, yes, and replace it with something that implements the same identical interface, but it's not actually going out to the network. It's not actually going to the database, right? I can simulate it. And now that I can simulate it, right, I can test it independently of an actual database or an actual network. Make sense? Right, so we're going to be drilling repeatedly over and over that we want all these pieces to be replaceable. Right? Well, I should be able to just take that out and just replace it with something else. And the way we do that is with interfaces. Yes? Right? We write all our code in terms of an interface, right? So that we can always replace the actual implementation with a phony or fake implementation. All right? And we can test it. So in this case, the interaction is decided. The behavior is decided by the controller, right? And we'll see how we can deal with that. Asynchronous controllers are those that the controller is not the one who who implements the particular sequence of events. It instead is the user. The user is free to send all sorts of events, right? As they click and drag and they interact with the user interface, there's a buffer of all these events, right, being sent over to somebody who's consuming all these events, right, and sequencing them and then sending them to the right place, right? So the controller are written in a different way, right, to consume this buffer of events, right? It is not the controller that says, this is what should happen next, and you can only do that, right? It's the controller now trying to have a conversation, an asynchronous conversation with us, right? Consuming this buffer. Typically, they're built by using methods that are invoked as callbacks to events that are tied to all sorts of either clicks or keystrokes or mouse movements, right? That are called in by the as events are being queued off interpret from the queue. GUIs is a very common implementation of this strategy, right? That try to decouple this low bandwidth interaction of the user, right, with this high bandwidth conversion from the analogical world, right, to some digital world, right? And we have this buffering, this conversion between the two, right? So yeah, so GUI is the most common example of asynchronous controllers. Who gets the ball rolling? So up to this point, we haven't really implemented an application that can run as a standalone application, where you can maybe run it from the command line and it can run on its own. Really, today we'll introduce the main method. Or did you do that yesterday? Oh, you did that already. Okay. All right, so we'll just really quick go over that, where we can where we'll be able to instantiate controllers and models and all this and glue this thing together, right? And tell everybody who's going to be talking to who, and then we'll kick off the implementation from there. So it'll be the main method who kicks this off. Something like this, where the main is be responsible for instantiating the model, instantiating the controller, telling the controller who the model is, and providing the view so that the controller can read from the view, send events to the model. The model can then operate on those events. The model can then send data back to the controller, so the controller can provide it to the view, and the view can then render it for a human consumption. Up to this point, we'll use a really simple interaction with the user. It's just keyboard, right? Just interacting at the console, where the user types something at the prompt. It's parsed as integers or booleans or strings or characters or whatnot, right? And then fed to the controller for consumption. And on the way out, right, we'll use things that's simple as just system out that print to display for humans. Okay, and that's going to be one of the first challenges, right? Humans is needed to run this, right, to interact with the controller, and that's going to be a challenge that we need to be able to deal with, because in testing when you're going to test this, you can't rely on an actual human being there and actually typing and reading. Humans are very slow. We would like to be able to run hundreds, thousands of automated tests, without the need of human interaction. Right? Humans are not reliable. We're messy. We forget things. We mistype. So instead, we want to create a consistent mechanism that we can test this. So at some point, we're going to have to override or substitute or replace or mock, right? Mock this system out and this scanner with implementations of our own, so that we can test. Okay. Mocks, as I mentioned earlier, is a strategy that we're going to introduce today of being able to replace or substitute or simulate something that we're not really interested in. that we might only really care about the algorithm that we want to test, yes? But that algorithm might have dependencies with other things that, again, might be hard to have access, like networks and databases or file system or an actual human being. So we want to mock those. We want to simulate them, yeah? Another use for mock system, the mock strategy, is to, if you have two systems that have to talk to one another and kind of like depend on each other, that, well, I can't build this until I have that. Ideally, oftentimes what you do is that, well, mock it, simulate it. It doesn't exist really, but I can simulate what it would give me if it did exist. Right? So I can stub it out, and it says, well, I know this is going to be a function that I need to call, and I'm going to expect this array with these objects, with these values. It doesn't yet exist. The algorithms don't yet exist, but at least I could, just maybe build maybe hard code the response, yes, and just respond that when I call the method. This allows me to separate the implementation and say, well, you deal with that part, and I deal with this. Meanwhile, while we're working separate, right, I'm going to mock your part, yes, as if it actually existed. It doesn't. I can mock it so I can continue working. I don't have to wait for you. Yes? Makes sense? So mock is also very, very useful for breaking up large systems and each one working on separate parts of the same feature. Yeah, so emulates components that are being worked concurrently, or tests something that requires I/O or requires database access or file I/O or whatnot. Okay. Yeah. So we're going to design and build our application always with that in mind, right? This needs to be written in such a way that can be tested, right? Ideally, when we start building something, we're going to have, there's going to be a requirements phase, right, of whatever project that you're working on. There'll be a requirements phase where folks are going to be busy meeting with everybody and writing down what everybody's opinions are and whatnot on what we should actually build. And usually those requirements eventually are going to become, those requirements are going to be written in human format, yes? The system shall do that and the other, right? It will be written in some human format. Those typically need to be converted in some formal test, right? Some formal test that can validate whether indeed the system is fulfilling that particular requirement, yes? So something that is amorphous and vague in human language needs to be written in some formal representation of actual code, yes? And ideally, that's the first challenge, right? Is the requirement concrete enough to be converted into something formal, right, in actual code? And you should always push back on as developers, we should always push back and say, well, that requirement is too vague. I can't actually represent it in code. I need a little more meat. I need a little more details, right, before I actually code it. So that's going to be our first challenge. It says, we're always going to be, whenever we write something, we need to write it in mind that we need to test it, right? We need to say, what's the requirement? Can I test it? Can I mock it? Can I replace things so I can automate these tests? I can't rely on a human being testing this. I need to be able to simulate that user, right? So we're always going to have thinking of our design is always going to have mock, right, in mind. How do we test this, right? So whenever we code, we're not going to code in terms of any particular implementation. We're always going to code in terms of some interface, so that we can replace the interface. Not the interface. We can replace the actual implementation, right? And with something that can be mocked. Okay. Standalone programs.